Hello everyone and welcome to another video. Today I'd like to talk about block diagrams, which are a critical and incredibly useful tool in the world of controls and systems engineering. We'll start by discussing and introducing a block diagram and showing why it's useful for describing a large complicated system. We'll then spend the majority of the time today here talking about block diagram algebra. This is also sometimes referred to as block diagram reduction, and we're going to see that it is a technique to take a large complicated block diagram and compress it down to a smaller, more simplified diagram. If you haven't already done so, please take a moment to watch my previous video on transfer functions here. We're going to see that transfer functions are incredibly helpful and a very useful tool when developing a block diagram and performing the subsequent algebra/reduction. You can reach that video by clicking on the link right up here or from the URL in the description of this video. So, if all of this sounds like more fun than a season's pass at Disneyland, let's jump over to the whiteboard and get started. Okay, so why don't we jump into block diagrams here? And maybe the easiest thing to do here is just start out with a definition here or a brief description of what is a block diagram here. So a block diagram is really, it's a graphical representation here. So let's just write this down. So a block diagram is a graphical representation of a system where we have smaller blocks which represent the functions of smaller subsystems within this larger system, as well as arrows or connections illustrating how signals flow between these subcomponents here, right? So a block diagram is a graphical replication of a system broken down into multiple subsystems, aka the blocks here, right? These are known as the blocks, as well as connections. Typically these are drawn as arrows, showing signal flow between components. So sometimes these are actually referred to as well as signal flow diagrams, block diagrams. All of these sort of mean the same thing here. So I think the easiest way to understand this here is maybe let's look at an example of this, of a real world system, and think about how we can draw this as a block diagram here. So let's look at an example here of your cruise control. How about? So this is a system that I think everybody is fairly familiar with, and just to refresh your memory here, I got a little prop here. I actually quote unquote borrowed my daughter's little toy car here. So the idea here with the cruise control is, right, you've got a vehicle, you've got a car here, you can step on the gas or set the throttle and the car will go faster or slower, right? You guys have all driven cars. I hope there are no middle schoolers watching this video, but if so, go out to your mom's car and check out what it does, right? You step on the gas, you make this thing go faster or slower here, right? And the idea with the cruise controller here is I'd like to build some sort of system so that I don't need a human in the loop here to adjust the speed here, right? So I can take the driver out of here, right? So sorry, Katarina Kitty Cat, we'll get rid of you. And the computer will be able to keep the car and maintain the velocity here by somehow actuating the throttle and somehow measuring the speed of the car and doing some calculations and basically taking appropriate action so that if this car goes up a hill or down a hill or the environment changes, basically the speed will be maintained, right? So that's the idea with a cruise controller. Why don't we see if we can take that description that we just spoke about here, about describing it, and instead of using words to describe how the system operates, let's use a block diagram or a signal flow diagram to show how are this one giant cruise control system made up of a lot of smaller different subcomponents here. So keeping this example in mind, let's go back up to the board and maybe let's just start drawing out some of the components that are relevant in here. So you probably have, like there's an engine in a car here, right? So why don't we just start here and call this like an engine, right? So this block might represent the engine, and this engine might have inputs and outputs here. So again, if you haven't watched the transfer function video here, I would recommend you do that real quick, because we're going to start thinking about this engine here as a black box or it's just some input-output relationship where you stick something in and something else comes out. So with an engine, you might have like a throttle setting. So this throttle setting might be between 0 and 1 here, and what the engine does is it will respond to that throttle setting, and maybe the crankshaft coming out of the engine spins at a certain speed, you know? So we could think about making a transfer function or a relationship between throttle and maybe crankshaft speed. Right? So here's one block here in my diagram, but we need more to describe this entire cruise control system that we were just discussing here. So, you know, this crankshaft then goes into maybe like a transmission. So maybe let's draw another block here, like a transmission of your car. Right? So the crankshaft spins at some speed here, and what comes out of the transmission is like a torque. Maybe we should call it the wheel torque or something like that, right? It's transferred through the transmission to the axle, and it will turn itself into a torque here. Well, that torque is going to be somehow transmitted to the pavement, and that will generate a force or a speed to move the car forward. So we could think about trying to generate another transfer function or another block here, which would maybe be the car dynamics, let's call it. Right? So some torque on the wheel, depending on the state of the car, is going to result in some velocity. Or actually, you know, instead of velocity, maybe we should call it speed here, because I guess, you know, with a car, usually you specify a speed, not a velocity vector here. So let's just call it speed, right? Okay, so how are we going to make this into a cruise control system here? Well, the idea then is, okay, you need to take this speed here, and now maybe we need some kind of sensor that would be able to measure the speed, because you know, the car is moving at some velocity. Maybe you need a rotary encoder, you need GPS, or you need some other system to understand what is actually the car doing. So maybe what you need here is you need some, maybe like a rotary encoder. Let's just use that, rotary encoder. This is basically your sensor. And I guess if we want to get even more specific, you need like a speedometer, right? This is your speedometer. It's basically a sensor which takes the actual speed here, and you can then get the measured speed. Right? And again, there might be some, all of these blocks, the idea here is there might be some dynamics, or there's some input-output relationship between each one of them, but by writing this in this diagram, right, we can focus on just tiny little pieces one at a time and then compose a larger image. So again, sorry for getting sidetracked, let's keep going here. What would you do with this measured speed? What you would probably do is you would come back here and maybe let me get a little bit more room here. Compare this with like a desired speed, right? So if you want to be going 60 miles an hour, but you measure that you're only going 55 miles an hour, that is going to generate some kind of error signal, right? And what you do with a cruise controller is that error signal, you're probably going to feed it into some computer on board your car here, which is effectively your cruise controller here, right? So this is your cruise controller, right? Because depending if you're going too fast or too slow, it would actuate the throttle appropriately here, right? So this larger picture, like we talked about here, this is sort of a composition. It's like Voltron, right? You got these tiny little components which by themselves are not that great here, but when they combine like Voltron, you can make a larger, more complicated system here, right? So this is all we mean when we're saying a block diagram here. A block diagram is basically a list of subcomponents and how they all interact together with one another here. Okay, now the reason this is relevant and the reason I keep talking about the transfer function discussion that we had earlier is usually with a block diagram here, one very convenient way to express or represent each one of these small blocks is with some kind of a transfer function. Now, it doesn't have to be a transfer function, right? This could just be some like static gain, or it could be a rule, or it could be a difference equation or a differential equation, but for our discussion, let's consider that most of these are transfer functions, because again, a transfer function, like we talked about earlier, does really well at modeling just the input-output relationship between, for a system here, right? And as you can see here, this is exactly what you want, right? All you care about is the input-output in a block diagram or a signal flow chart here, okay? So, for example, this controller, you know, maybe let's call this like some transfer function C of S. Maybe this is like a G1 of S, G2 of S, G3 of S, and maybe the sensor, let's call it H of S here, right? So again, we could represent all of them as transfer functions if we wanted to, okay? So here's a general picture of what a block diagram is. Again, it's just a graphical representation of a large complicated system broken up into small little blocks, as well as how all those blocks are connected. Now, let's get a little bit more formal here and talk about the different things you see here. We see some blocks, we see some of these summing nodes, we see some of these branch points, things like that. Let's talk about this real quick before we go into the meat of the discussion and talk about block diagram algebra. We need to set a little bit of some foundational components here, okay? And what I mean by that is when I say components, let's talk literally about what types of components you might see in a block diagram here. So let's chat about block diagram components. Okay, so the most important one here is obviously a block here, right? So this is a block, sometimes also referred to as a subsystem or a transfer function, whatever you'd like here. But the idea here with a block here is that it has certain inputs, let's call it U, and it has certain outputs Y. So again, here's your input and it has your output, okay? So all a block does here, right, is it just represents a subsystem. And the nice thing about this is you can now just focus all of your attention on just developing this one little subsystem here, right? It's like a tiny part of your system here. So all this thing does here is that it models one component of the larger system. So again, like we talked about earlier, it could be a transfer function, it could be an ODE, it could be a difference equation, it could be a state flow diagram, it could be a discrete event system, it could be any mathematical model you want, as long as when you put something in, you get something out, all right? So not a lot of requirements on that, but again, we'll see that the one that we're mostly interested in is we are going to be talking a lot here when you do model this thing as a transfer function. This is going to be very useful for some of the upcoming discussions here. So if I were you, I would recommend you model these as transfer functions here, at least to start out with, okay? All right, what else might you have in a block diagram? We saw there was this block that I drew earlier here, and this is also very common here. So you'll see things like this. These are typically referred to as summing nodes or summing blocks here. So this is here is a summing node, okay? And usually what this thing does here is they has two or more sort of quote-unquote input nubbins, right? This is where something goes into it, and then you'll have something coming out here. So again, you might have a U1 and a U2, and out of this, you might have some output Y here, right? And the idea with a summing node here is it's really, really simple here. It's just a graphical representation of an addition or a plus or a subtraction here. So in this case, in this example here, all this node represents is that the output here is U1 minus U2. And usually you can see that depending on the signs, you know, maybe this is a plus, maybe you have more than one here, but all it does here is it's a node which takes multiple signals in, adds or subtracts them appropriately, and sends one signal out. One thing you may want to note here is that in your signal flow diagrams, because of the nature of it, it's just adding or subtracting here, you really want to make sure that one very common mistake here is if you don't have the same units, like coming back to our cruise controller here, right? What if you specify the desired speed in miles per hour, but your speedometer, you purchase that thing from Canada, and Canada spits everything out in kilometers per hour, right? Kilometers per hour, right? Now you've got a problem because you really can't subtract two things of different units without some kind of conversion. So you may need a small block in here whose sole job in life it is to convert from kilometers to miles per hour here, right? So something just to be aware of. So again, let's just make a note here. Ensure all signals have same units, right? Because in a block diagram or the signal flow chart, right, all of these signals could have completely different units, right? We said this is a speed, right? The difference between two speeds is another speed here. But this throttle setting is like a fraction, something between 0 and 1. Crankshaft speed, maybe that's angular velocity. Wheel torque, that's Newton meters, right? Speed, you know, I think you get the point, right? You can have different units, just be a little bit careful, okay? Okay, what else can you see in a block diagram pretty commonly? Like, let's zoom into this little region right over here. So you see here, this is what's referred to as a branch point or a branch node. So what that looks like here is you might have a signal here, right? Let's call this signal, I don't know, maybe E. Okay, and you want this signal to go more than just one place here. So you may want to branch off of this and send the signal somewhere else. So this little point right here is typically or sometimes referred to as a branch point. Here, and I don't know if we need to explain this anymore. All of these signals are E, right here. The only way you change a signal in a block diagram here is you either have a summing point or some other block / transfer function which changes the signal. All this is doing is it's literally like splicing another wire onto the line. Like I like to think of block diagrams almost from an electrical perspective. If you think of this as an electrical circuit, right? This is a line carrying I don't know, like the error in velocity of your cruise controller, and maybe you want to send that to the computer, but maybe you also want to send that signal to a data logging unit or something like that here. So yeah, that's pretty much it here. So I think what we can do now is, within this context, I think we've got a good idea of what does a block diagram look like here and what are the major block diagram components. Let's take our next step here into block diagram algebra. And actually, maybe let's keep this picture up here, and I'll just change the title here so we can talk about our next component, and this would be the meat of the discussion here today here. Let's talk about block diagram algebra. Okay, right, and we said that this is also known as sometimes block diagram reduction. Okay, so the concept with block diagram reduction here, or block diagram algebra, is that, all right, you might have this complicated block diagram here, right? This is actually what's going on under the hood of your car, right? Inside the car, you've got, you know, an ECU, some electronic control unit, you've got engines, you've got transmissions, you've got car dynamics, you've got sensors, you've got all this junk going on. But you know what? You as a driver or as a user, I don't care about all this stuff that's happening underneath the hood. I just want to make sure that when I tell the car to go faster, it actually does go faster here, all right? So what I'm basically getting at here is, really, you don't care about what's going on under the hood here. So if I were to sort of encapsulate all of this sort of in a larger block, let me use this red, this kind of red, which is on its way out, it looks like. Boy, oh boy, I maybe need a new red pen here. All right. But what I want to be able to do is, can I somehow combine these blocks here or do mathematical reductions here so that I can make this entire thing, everything that's inside the red, what I want to do here is turn this into something simpler, where maybe I'm going to call this let's call it the closed loop system, where you put in the desired speed, right? And out comes the actual speed of the car here, right? Because from an input-output perspective, if you think about this, right, that's what this upper diagram does, right? All you do here is you tell this system how fast you want to go. It does all of this gobbledygook underneath the hood, right? And it makes the car go the speed you want it to, right? Sure, it's not instantaneous. There are dynamics and there's relationships between how fast you want to go and how fast you actually go here, right? But it's all of these relationships, right? Can I compress all of those into maybe one single block? Maybe let's call this like a T of S for a closed loop system here. One block which also represents mathematically the exact same relationship here. So basically, this block, this complicated block diagram up here, can I make it equivalent, or can I find one single block which is exactly identical and equivalent to it here, right? That's the concept of block diagram algebra here, and that's what I want to talk about now, is how can we take something that's complicated like this with many, many blocks and compress it down to a single block, okay? All right, so tell you what we should do here is, what I want to look at now is a couple of smaller operations. So the way we're going to get to this here is we are going to look at how can I combine two blocks, or maybe a block and a summing node, or a block and a branch point. Like, let's look at how can I make reductions in small little components of the diagram before we jump over and tackle the large one, okay? So give me a second here. I'm going to pause the video and erase the board, and we'll come back in just a second. Okay, so what I'd like to do now is look at a series of different operations on block diagrams. And the first one that I'd like to do here is called the combine in series operation. So what that means is, let's say you've got a block diagram here where you've got two transfer functions, or two blocks here, just lined up in series with one another here. So you've got a G1 of S and a G2 of S lined up like such. Okay, what I want to do now is see, is there a way that I could make this equivalent to just a single block here, right? So the question is, what is this single block that would have the exact same input-output relationship as my original block, okay? So the way I think we can go about doing this here is, let's just go ahead and draw a little dashed box here, maybe, around the original system here, right? Okay, so this system here, you can see, let's go ahead and label some of these signals here. Maybe let's call this x1 of S. Here's x2 of S. And here's x3 of S. All right? So what I need to make sure is that this equivalent system here has the same input, which is x1 of S, and has the exact same output, x3 of S. Right? That's what I need to ensure. Okay? So let's come over here on this first block and look at what is the relationship between x1, the input, and x3, the output. And now this is where using transfer functions as each one of these individual blocks is going to be very useful here. Because if each one of these is a transfer function, I can make the observation that, okay, what is x3? x3 is just the transfer function multiplied by the input, right? Because that's exactly what a transfer function does, right? The way you get an output from a transfer function is you take the transfer function itself and you multiply by the input. Okay, so let's go ahead and just write this down. So we see here that x3 of S, this is nothing more than G2 of S times x2 of S. Okay? And again, be a little cautious here. If you notice here, I didn't flip the order. You might think that multiplication, who cares if it comes one before the other here, right? And you would be right if these were scalars here. Meaning, if all of these signals were just one by one vectors here, right? But we're going to see later on down the road that these might be vectors here. They might be more complicated here. So order of operation is going to matter here. So let's just keep it in the proper order, right? It's transfer function multiplied by the input here gets you the output, okay? Okay, so great. Let's take a look at this. Now, let's go one step further here, and we can make the note here, and we can see here that, you know what? What is x2? Let's just walk one step back. x2, this is just transfer function multiplied by its input here. So in other words, x2 of S is nothing more than G1 of S multiplied by x1 of S, right? Great. So let's plug this relationship into here, right? And we end up with, well, I still got the G2 here of S, and now I've got G1 of S times x1 of S, right? This gives me the output x3, right? So if you look at this now, you see that, okay, the output of the entire system is something, let's call this thing right here maybe T of S, right? Times the input of the entire system here. Okay, so we see that this here is actually what should go in this block here, right? So this is now the composite block G2 of S times G1 of S, right? And again, be a little cautious here on the order here, right? You might be very tempted to just say, okay, it could be G1 times G2, or it could be G2 times G1. Who cares? It does matter here later on down the road when we start thinking about multi-input, multi-output systems here. So let's just be consistent here and write it G2 times G1, which is the proper order, right? So great. That's how you would combine two blocks in series. So what you can think about now is, anytime you see two blocks one after the other here in a block diagram, and you want to smash them down into a single block, just multiply the two blocks together, right? Okay, great. So let's look at another operation here. Maybe let's just, maybe let's see if I can divide this board in half, and maybe we'll kind of flip-flop between here. So here, operation number 2 here. How about the operation of moving a branch point moving a branch point ahead of a block. So again, branch points, sometimes these might also be referred to as pick-off points. And I think you'll see why here in a second here. So what that means here is, let's say you've got a block diagram that looks something like this. You've got a transfer function or a block here. You got something coming into it, and you got something coming out of it. And then there's a branch point here where the signal gets picked off and sent somewhere else here, right? So again, here's this pick-off point or this branch point, however you want to think about it. Now, what I want to do now is, can I redraw this now as some equivalent where what I want to do is move this pick-off point in front of the block here. So what I would like the equivalent system to look like here is something like, you got the block here, here's G of S, and now you got the pick-off point coming here. And what you're going to end up seeing here is we're actually going to need to put in a G here. Here's G of S, and then you get the output. Okay. So what we claim is these two should be equivalent here. Okay. Let's just check that for ourselves. So again, the easiest way to do this here is to go ahead and label this. So you got x1 of S here, and then you have x2 of S here. Right? And using the property of branch points, we see that this signal is the exact same thing as this signal. So this is also x2 of S. Right? So again, if you want to use like a red marker or something like that and kind of draw a dashed box around the original system, right? You see that I don't care what's going on underneath the hood, like underneath this red, inside the red dots here, as long as when I put in x1, I get x2 coming out here and x2 coming out here, okay? So let's go ahead and check, is that the exact, is that true over here in the equivalent diagram, right? So again, you label this, here's x1, and then we got to ask, what is this signal and what is this signal here, right? Does it match here? So let's look here on the left. So over here we see that this signal over here, this is going to be, let's call it just something here for now. This is going to be the transfer function, G of S, right, times x1 of S, right? That's what this signal is over here. And again, if you look, that's exactly what is going on in the original equation, right? And the better name for that signal here is actually x2 here, right? Because x2 is the output of the transfer function g. So here, this is also x2, right? So that matches. And then similarly, this signal down here, you see that basically what this signal is, it's the transfer function g times its input, which is x1 here. So this is also x2. Great. So we see that these two diagrams are equivalent. So what you can do here is anytime you see this in your block diagram here where there's a pickoff point behind a block and for some reason you want to move it in front, you just redraw the diagram like this. Or vice versa, right? If you see something like this and you want to move this pickoff point or this branch point behind the block, you can just do this, right? This is a two-way arrow, right? It's equivalent in both directions here, right? So great, that's another operation. Let's keep going here. Let's come over here and maybe erase this side here and come up to operation number 3 here. So operation number 3 is going to be, well, let's just do the opposite. Like, what if you wanted to move a pickoff point behind a block for some reason, okay? So that's very similar to earlier here, but let's say let's move a branch point or a pickoff point here behind a block. Okay, so what that means here is, all right, you got a diagram that looks like this. You got a G of S here. And the branch point is in front. Something like that, okay? And what I'd like to do now is make this equivalent to taking this branch point and moving it behind the block. So now you got this here. And then what we're going to end up doing here is you're going to see that in order to make this equivalent here, you're actually going to have to put in G inverse. Maybe I'll write it G inverse of S. Maybe it's a better way to write this. G inverse of S. Okay? So again, the way to check this thing is, again, just draw the interface to this block here, or draw the input-output relationship here to this block. Right? So the original system here, let's label some of these signals here. You had x1 of S coming in, and here let's call this thing x2, which is just the transfer function output, and over here you got x1 of S. Okay? okay? So you better hope that if you did it right, the interface to this block is the exact same thing, right? Meaning the input and the outputs are the same and their relationship is the same here. So let's just check this. So here's x1 of s. We know for a fact that this has got to be x2 of s, right? Because x2 is defined to be just the output of transfer function g, and this is definitely what this is. Now over here, this is interesting. What is this signal right here? Okay, so we got to be a little bit careful of this here. Okay, so maybe let's call this thing something temporary. I don't know, P of s. Okay, what is this signal? So this P of s, right? Okay, how do I get this? This is the output of this block here, this transfer function. So the way I get this is I go ahead, and how you get the output of this block is you take the block or you take the transfer function and multiply it by its input here. So this is apparently what we're calling G inverse of s times x2, right? Okay, now let's go ahead and again, what is x2 here? x2 is this transfer function multiplied by its input here, right? So let's just do that here. So again, this x2 term, maybe I'll put this in brackets here, right? So x2 is going to be g of s times x1 of s, right? Okay, and now let's maybe get, if you get rid of these braces here, right? This here might want to give you a little bit of pause here for a second here. What the heck is this thing that we wrote g negative 1 of s here, right? This is basically saying that we hope that its inverse exists, right? Anytime you see inverse, I'm sure hopefully something not a red flag here, but some caution bells start ringing in your head, right? Inverses, you should always be asking, do they exist? Are they a one-to-one mapping? You know, all these kind of standard questions here. So let's just assume that this inverse exists here and that there is a one-to-one mapping here. Again, this might not be the case for a multi-input, multi-output system here, okay? So if it does exist, then hopefully this just evaluates to an identity or a 1 in a scalar case here, right? And we end up seeing that this P of s signal is actually indeed x1 of s here. So this here, instead of calling it P of s, we can call it x1 of s, right? And now the left-hand side input and outputs is exactly equal to the right-hand side inputs and outputs here, right? So again, with this slight caveat here, we can see that these two diagrams are identical. So if you want to take this branch point and move it behind the block, you can definitely do that. You just need to do this g negative 1. You just need to calculate the inverse of the transfer function, which again, in a scalar case, is literally the inverse. It's just a reciprocal of flipping the numerator and the denominator here. But again, that might also have some issues here, but long story short, this should work here, right? Okay, great. So we said that's how you could move a pick-off point behind a block. Let's keep going here with our list of operations and how we can do different things. So what are we on to? Number 4 here, okay? So number 4, the fourth operation you can do, or the fourth base manipulation here, is what about moving a summing point ahead of a block here? Okay, so moving a summing point ahead of a block. Okay, so in other words, what I mean by that is, all right, you got in the original block diagram, you got g of s going into a summing block here. But let's just make them both pluses for now. And maybe you know what? That's fine. Yeah, let's leave it like this for now. Okay. Okay, and then something like this. Okay. So again, here's the original block here, and now what I would like to do is make its equivalent block here. And what you're going to see here is that, okay, this is going to have to look something like this: plus plus g of s, and then g inverse of s. Oops, let me write this clearly. There, okay? Okay, so we claim that these two are the same. Okay? right? So in order to move this summing block in front, you've got to go ahead and do this G inverse. So again, same check just to prove to ourselves that this is true. Let's just go label all these. So here's x1 of s, here's x2 of s, and here's x3 of s, right? Okay, so we need to make sure that the exact same thing occurs over here. So you have x1 of s, x2 of s, and x3 of s coming out the far side. Okay, so maybe on the left-hand side, let's just go ahead and compute what's the relationship here between the inputs and the output of this block here. So we see that, all right, x3 of s, right, we can just read it from the block diagram. x3 of s is this signal plus this signal. And this signal right here, I think you would agree that this is g of s times x1 of s, right? That's this signal right here, plus x2 of s. Right? Okay, so that's the relationship between the inputs and the output of the original system. Now, what about over in this what we claim is the equivalent system here? Okay, so now in the equivalent system, let's take a look here. We see that, okay, x3 is going to be g of s times this signal right here. Maybe to temporarily call this, let's call it p of s again. Right? This signal coming out of the summing block, let's call it p. So, all right, x3 is g of s times p of s, right? Okay, now we got to ask ourselves, what is p? P is this signal plus this signal here, right? And again, this one right here, you can get it by the transfer function multiplied by its input. So again, sorry for skipping a step here, but I think at this point it's a little bit trivial. Let's write p here. P is going to actually be what? It's x1 of s plus this thing right here, right, which is g inverse of s times x2 of s. Right? Okay, so now let's distribute the g through. And again, remember, I'm being very careful on left multiplying or right multiplying here, because we claim that later on it might potentially matter. S x2 of s. Sorry, I'm running out of space here. I think hopefully you can see that. Okay, so now hopefully this guy just turns into a 1 because we're dealing with single input, single output systems, because I got a g times g inverse. So we end up with a relationship here that on the left side that you got x3 of s is g of s times x1 of s plus x2 of s. Great. And if you look here, we can compare and see that, yes, indeed, on both sides here, right, that's the relationship between the input and the output. They should have the same input-output relationship here, right? So that was that should work here. Okay, so again, those two are equivalent diagrams. Okay, let's do the reverse here. So number 5 here would be, how about moving the summing point behind the block? Oh, sorry, and maybe we should have made one more note here. Sorry, before we leave here. Depending on the sign, the sign of this, so for example, like what if this was a minus sign instead? If that was a minus, right, you would just have to go through and see that, okay, that would change this sign right here, right? So obviously over here, you're going to have to modify the sign, the sign of this sum as well. And it turns out what you need to do here is just make sure that this is the same sign, right? So just got to make sure that the summing block, their signs, signs, match, right? Because if you change that to a minus, that changes this to a minus, which changes this to a minus, which changes this to a minus, and we still have equal input-output relationships here. So again, sometimes what you'll see is you'll see this written like plus minus and then plus minus, meaning that this input here, right, it can be a plus or it can be a minus. Just make sure that the signs match here. And keep that in the back of your head. We're going to see this again in just a second, okay? So sorry for that little side detour here. Okay, let's come back to number 5 here, right? So number 5 here was moving a summing point behind block here. So moving summing point behind block. Okay, so what that looks like here is, let's erase our picture. Erase this old diagram here and start again here. Okay, so number 5, we're moving it behind the block. So now what you've got here is you've got a summing point here, and let's use our notation earlier that we just talked about here. Let's say plus minus. This second input can be whatever you wanted, a plus or a minus here. Okay, and this is now g of s, like such. Okay, so here's my original system here, and now what I want to do here is move this summing point behind the block, so I need an equivalent block diagram over here, and you're going to end up seeing that, okay, the way to do this here is g of s here, you move the summing block over here, and again, you keep the signs matched up in this second input, and what you actually have to do is just put in another g down here. Great. And again, we'll do our little trick like we did earlier, is just encapsulate everything under the hood here, or encapsulate these small diagrams, and make sure that the input-output relationship of these things are the same. So again, here's x1, here's x2, here's x3, and we got to make sure we end up with the exact same thing, x1, x2, x3. So again, over here on the left here, we just say that, okay, x3 is just going to be g times this thing, which is going to be, what, it's x1 plus or minus x2, right? So again, distribute that if you'd like here, so you end up with g of s, x1 of s, plus or minus g of s, x2 of s, right? That's the relationship between the inputs x1 and x2 and the output x3. Okay, let's make sure we have that exact same relationship on this side here. So again, starting with x3, right? We see that x3 is this signal right here, which is what? It's going to be g of s times x1 of s, right? Plus or minus this signal here, which is g of s times x2, right? And oh gosh, I guess you don't even have to do anything, because if you stare at these two, you see that, yep, those two are the exact same input-output relationship here, and the plus minus sign again is properly accounted for here. So again, these two diagrams are equivalent here, right? You can either do this or you can do that. Okay, let's keep on rolling here. That was number 5 here. Okay, now let's get to 2 of the very interesting ones here. Okay, so number 6 here. This is going to be what we are going to call eliminating a feed-forward loop here. So in a lot of times with controls, and a lot of the times you've heard of feedback loops here, but you know, a feed-forward loop is another kind of loop that you can encounter. So let's just do this here. So 6 here is eliminating a feed-forward loop. Okay, so what that looks like here is in the original diagram, let's say you got something like g of s, and this goes into a summing block, plus minus. Okay, and then what you've got here is another path as well. Let's call this thing like an h of s, another transfer function, or another block here. This goes in, and then comes in and combines like this. Okay, so here's the original diagram. This lower component, well, I guess depends on how you look at this here. You can think about this as a feed-forward loop in the sense that there are 2 signal paths that go forward here to produce an output path here, right? So what we want to do here is figure out what is the equivalent. In this case, we can get a single block. So instead of writing this thing as 2 separate, or actually 3 blocks, right? Two blocks and a summing node, you could write this as just a single block here, right? So let's do our little trick here and say, all right, here's the interface that I want here, right? I want to be able to spit in a single value x1 of s, and then out comes x2 of s, right? So all I got to do here is let's start on the left side here and just compute what's the input-output relationship between x2 and x1. So if you look at this, what's x2? x2 of s. It's just this signal plus or minus this signal. So again, I guess we can call this P1 and P2. So here we go. This is P1 of s plus or minus P2 of s, right? Okay, what is P1? P1 is just transfer function multiplied by its input. So this is g of s times x1 of s, right? Plus or minus, what is P2? P2 is transfer function multiplied by its input, which is x1 of s, right? Okay, let's pull out or factor out x1 on the right. Again, sorry for harping on it here, but I want to make sure we're pulling it off with the idea or in the back of our head that these h and g's, these might be matrices here instead of just scalars, okay? So what we end up with, this is just g of s plus or minus h of s, right? And then we can pull x1 of s out. Okay, so here we go. Here's our result here, right? Here's the input-output relationship of this single block here. So we see that, you know what? To get the output of the block, it's you multiply by this combined transfer function by the input here, right? So what this thing right here is, we see this is nothing more than g of s plus or minus h of s, right? And again, the plus or minus matches with this plus or minus here, right? Okay, great. So let's do our last one, and this is probably one of the most interesting ones that we're going to encounter here. We just looked at the feed forward loop, but in controls, the much more famous sibling of that loop is the feedback loop. This is what we're doing all day with control engineering, right? Is, okay, item 7 here is, how do I eliminate a feedback loop? Okay, so here's the architecture here. Plus, and again, tell you what, let's keep this thing as your typical standard minus sign here, okay? And I'm going to talk about this again in just a second here. So, okay, you got a g of s, and then you have another potential block here going in like this, okay? And same game that we just saw with the feed forward loop, I want to crush this thing down to a single block here, which has an input of, let's call this thing x1 of s, and coming out of this is x2 of s, right? So I want the exact same interface. So the question again is, what is this block in here, okay? So like we did earlier, we're going to keep doing this. I think you're probably going to get sick of me drawing these dashed red boxes all over the place here, right? But that's the idea. Okay, I need to look at this. So let's label this intermediate signal here as E of s, right? It's the error between, or this minus this, some kind of difference, right? So let's think about this. Okay, x2 of s. Let's write this down. x2 of s is just going to be transfer function times its input, right? Okay, so now what is the E of s signal here? E of s is this minus this here, right? So this is x1 of s minus this signal here, which in this case is what? It's h of s times x2 of s, right? Okay, you know what we should do here? Let's go ahead and distribute the g through. Okay, so we end up with g of s times x1 of s minus g of s h of s times x2 of s. All right? Okay, and all this equals x2 of s. And you see, we end up in this sort of feedback scheme here, right? I see x2 over here and an x2, and you could end up chasing this thing's tail over and over and over and over, but here's the trick here. So what we're going to do is, let's move this to the other side here, right? This term, move it to the left side. So we end up with x2 of s plus g h times x2, right? That's the left-hand side, is equal to g x1, like that, right? Now, over here, what we can do is let's pull off or factor out x2, again, keeping in mind the idea that this might potentially be for matrices, pull this thing out on the right, okay? So we end up with, it's actually an identity matrix, or a 1 here. Again, I'm pretending that these things could be matrices, plus g, h, and here's x2 on this side, right? Is equal to this thing over here, right? It's equal to g of s, x1 of s. Okay? Now what I want to do here is, let's now assume that maybe the inverse of this thing in square brackets exists. So what I can do is I can left multiply by the inverse of this thing on both sides here to get x2 by itself. So this is going to be identity plus g, h, inverse times g, times, wait, did I? No, I think I got that right. Yeah, okay, times x1 of s, right? And maybe let me put this in curly braces, because we see this is the relationship we're looking for here, right? This thing within curly braces gets me the entire output of the system if I multiply by the entire input of the system here. So this thing in curly braces is what we can call T of S, or my closed loop transfer function. So what goes in here, in this question mark here, is we end up with a, boy, I should have written this thing a little bit bigger. You tell you what, let me do it like this. I'll just draw an arrow here. So this is identity plus G H, this thing inverse times G of S, right? That's what goes in here, okay? Now, if these things were all scalar here, you see that this inverse can kind of go on the bottom. So let me just write here that if scalar, if these are all single input, single output systems, you'll end up with this closed loop transfer function, right? This is what we're calculating right here. You end up with this T of S is G over 1 plus G H. Okay? So this, you might see this in textbooks, but again, remember that what it really came from is this discussion up here where we're treating them like they were matrices. So either way you can kind of consider it, but I like this better. This is the more kind of general form here, right? Now, here's the interesting thing here, and why I was harping on that sign, the SIGN earlier. You notice here, there's a minus sign here, but the closed loop equivalent thing has a plus sign here, right? So the sign flipped, right? Because we came all the way back down to this step where we moved everything to the other side and therefore changed the sign here, right? So what you might see this written as, if I want to write this as our usual plus minus, right? So the second input, it could either be a plus or it could either be a minus. The result here is it's actually I minus plus, right? So the sign is always opposite. So again, let me stress that one more time, and maybe I will circle this thing in green, because I guarantee you someone is going to make this mistake on a homework assignment or a midterm or some problem. This is a very common mistake here, right? That the sign, S-I-G-N, is opposite. Okay. Right? Okay. Great. So I think that gives us that gives us 7 tools in our tool belt on how to reduce a block diagram into simpler components. So here's what I want to do next here. Let's go over an in-depth example. I'll pause the video, erase the board, and then I'm going to write up an example of a complicated block diagram that we're going to apply some of these 7 different techniques to try to squash this thing down to a simpler block diagram. Okay, so give me a second and I'll be right back. Okay, so let's go ahead and look at an example of block diagram algebra. So what I want to do here is let's draw out a system over here, and I'll make it a little bit big just so we have enough room to work with here. So here, plus minus here. Let's make this go into some block here. Let's call it a G1 of S. And this is actually going to go into a summing block like such here. And actually we're going to pick off this signal and feed it forward up to here. Okay. And then what we're going to do is take the output of this summing block, stick it into another block. Let's call it G2 of S. And then we'll feed back this signal through a third block. Let's call it H of S. And then that will come back into this feedback loop. Okay, so here's our block diagram here. Let's call this maybe U as the input here, and all the way over on the other side is the output. So here's a quasi-complicated block diagram here, and what we would like to do now is see if we can turn this thing into an equivalent block where you just have a single block that you put in the input U and out comes the output Y, and we're looking for this closed loop transfer function T of S, which is the equivalent to that complicated block diagram over there. Okay, so the way we're going to do this is we're going to use a series of modifications to this diagram to apply some of those techniques we just looked at here. Okay, so let me do that now. Let's go ahead and maybe let me erase this because I think we understand the goal of where we're trying to get to. Let's go ahead and talk about a series of modifications that are going to make this feasible here. So let's do, how about modification number 1 here. Okay, so what we're going to do is let's move the sum block. Okay, so let's isolate what I'm talking about here. Where do we want to do a little bit of surgery on this block? So let's do this right here. I'm going to use our little dashed red lines to isolate a region. Okay, and actually, sorry, maybe what we should also do before we do this is, it's very helpful if we label some of these intermediate signals so we know what we're talking about here. So let's call this signal right here, let's call this maybe, how about x1? And let's call this signal right here x2. We'll call this signal here x3. Oops, 3 of S. And we'll call this signal over here x4. Okay, so those are the signals. Okay, so if we just isolate just those pertinent blocks here, right, we can basically redraw this. Let's just look at only the equivalent blocks here, right? So let me redraw that small section that's inside my dashed red line here. Okay, so it looks like this, right? Where you got U coming in up here, then you have x2 here, and then you have, coming out the other end, you have y, right? So this is exactly what we saw earlier, where you want to know, I want to move this summing block behind, okay? So we saw that earlier, that is exactly equivalent to this diagram, right? So if we apply that rule we developed earlier about moving a summing node behind a block, right, we saw that we can write this like this, right? Those two are the exact same thing here, right? So what I want to do now is we are going to replace that, or do a little bit of surgery of the thing that's inside the red box. We're going to replace it with this. So let me just do this. I will carefully erase only the things inside the red box, right? And we are going to replace it now with this picture over here. So what we got is you got U coming in like such, and then you got a G2 here. Then we have G2, and then these guys come into the summing block on the far side. Great. So we have not changed the functionality of the model here, right? That's exactly the same. It's the same block. Well, it's not the same block diagram, but functionally, and from a signal flow perspective, the input-output relationship has not been modified yet here. Okay. All right. Great. So now let's look at another modification. How about modification number 2 here? So the second thing I want to do here is, well, there are some blocks in series. So let's go ahead and combine in series. Okay, so what I mean by that is maybe we should now erase our red box because this is not what we're looking at anymore. Okay, let's see if I can find another area where we can do a little bit of engineering surgery here. And in fact, that's right here, right? If you look at, there's 2 blocks. This is some pretty low-hanging fruit. These 2 blocks are exactly in series. So again, let's follow our pattern here, and we see if I just redraw the things in the red box, right? You got G1 here, followed by G2, and out the other end, yeah, you got something like that, right? And we saw that, okay, from our discussion earlier, this is exactly the same as a single block here, where it's G2 times G1. And again, we're careful of the order here, right? Okay, so what that means here is the second modification I can do is we can erase everything inside this red box here, and I'm going to replace it with its equivalent representation of just a single block G2 times G1 of S. Great. Okay, so we're making progress. Perfect, perfect. All right, so now let me erase the red box because we're done. Okay. All right, let me erase this red line here. Perfect, perfect. Okay. Now, let's look at another thing that we can do here. How about, let's identify here, this summing block right here. And the red box is going to be a little bit non-standard here, but I think if we isolate this region right here, okay, what we can do here for modification 3 is we are going to now move the sum block, move sum behind a block. Okay, so again, let's redraw what we've got up there in the red box here. So you got a summing block here where you got a plus, minus, and then we have G2, G1, and then you've got basically this, right? So here's U, here's X4. Then I guess we didn't really, we've got some other signal up there. I don't know what we want to call it. I don't know, like an X5, something like that. But anyway, go back to your notes and you saw that this here, if I want to move this summing block behind, we can easily do that here by, first off, you got G2, G1, and then you got the summing block here. Okay, but what we have to do here is I have to put in actually G2 and G1 like this. Okay, so these two are equivalent. So again, I'm going to erase the thing in red and replace it with this representation here. Okay, so let's do that. So erase everything in red. And actually, shoot, maybe what I should have done is actually let me move the red dash line just so I have a little bit more space. What I mean by that is maybe it should have been better if I drew it like this. There we go. Okay. Okay. Perfect. Okay, so what I can do now is we are going to redraw this thing. Yeah, okay. So coming in, we now have, what do we got? We got G2, G1, plus minus, and then, shucks, I think I'm kind of running out of, this is not going to be the prettiest thing in the world, sorry. G2, G1. Wish I could shift everything over. But okay, anyway, I think that will do. Let me make sure I got that right. HG2, G1, yeah, minus. Yeah, perfect. Okay, so tell you what, let's go ahead and now do our same thing. Now we can erase our red box because we would like to look for what else we could make some modifications to. Okay. And actually, yeah, this is kind of bugging me. Let's just scoot this whole thing over. I wish this was in Simulink so that you could easily do this quickly, but I'm just going to scooch these blocks over. So I got G2, G1, and H. Let me see if I can remember that. So you got H here, and then you got G2 times G1. There we go, and then, okay, there we go. That looks a little bit cleaner. Okay, great. Okay, so let's keep going. Here we go. Another real low-hanging fruit. Another combine in series operation. So let's do modification number 4. So modification number 4 is I see another low-hanging fruit of combine in series. So what we got over here is you got H, then you got G2, G1. And again, we got to be a little careful. Pay attention to which direction the signal flows are going here, right? Because what this is going to mean here is I would now like to combine this thing into a single brick here, right? Which looks like it's actually what? It's G2, G1, H. Right? And we better double check that here. Let's call this just y3. Yeah, y3 is g2, g1 times this output, which is h times the input, y1. Right, so this is, yeah, g2 with g1h. Yep, okay, so we got it. We got the order correct. Perfect. Okay, so let's combine these guys here. I'll erase everything in the red, because what we're going to do is we're going to replace it with an equivalent here of just a single G2, G1, H. Great, okay. Doing well. Let's go ahead and erase the red box now and see what else we want to modify here in our diagram. Okay, so let's see. Oh, here's modification 5. This is something we didn't actually explicitly discuss here earlier, but I think you'll agree with me this is pretty trivial here. So let's see here. So modification 5 here is, let's switch the order of the sum blocks. Okay, so we didn't talk about this earlier here, but what I mean here is let's just isolate these two summing blocks here. So these two right here, okay? So if you look at these, and maybe it would behoove us to label some of these signals here. Let's say this thing coming in here is like x6. Let's call this x5. This line here is x5. And let's call this thing coming in up here. I just want to make sure I got the notation right. Yeah, here, let's call this x8. Okay, and then you got y coming out. Okay, so let's just look at the black, or sorry, everything inside the red here. Right? So if you look inside the red, we see that the relationship here of, let's draw this here. So you've got plus, minus, going into another plus, plus, something like this. And then you got y coming out this end. Okay, so let's redraw this, x6. And then coming down here, oh, sorry, I guess I missed, yeah, let's call this signal here x7. Okay, x7, and then you got x8. Okay. Okay, so let's look at the relationship here. So this is just a bunch of sums here. So you've got, what did I call this? Sorry, this was x5. Sorry, x5, right? Okay, so here, y is going to be what? It's x5 plus x8, right? x5 here is actually x6 minus x7. So you got this is what? x6 minus x7, and then the plus x8, right? Yeah, right? That's the relationship that that is original here, right? But I think you'll see that, you know, it doesn't matter if I switch the order of these blocks to look something like this. If I now have something that looks like this, plus, 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 minus, here's y, here's x6 coming in on the other side, and then I've got x8 here, and then x7 here. So if I just switch these order, it actually doesn't matter. So let's double check that here. So on the right hand side, let's look at the relationship. So I got y is going to be this thing minus x7, and this thing right here is going to be x6 plus x8 minus x7, right? So again, if you look at this, yeah, these two are exactly the same thing. Okay, so it's kind of block diagram algebra, but really it's just redrawing the order of the sums here. So what we can do over here is switch this thing to basically look like this. Let me switch this. Okay, so what we could do here is Boy, again, I really wish I had something cleaner here. What I want to do is, let's scooch this G2 further down here, right? So what I want to do is I want to move this all the way over to this side. So all I'm going to do is just move this over here, G2. Okay, something like that. And same thing, let's move this a little bit further downstream here. So this thing was a G2, G1H, right? Okay. Okay, so really, right, I haven't done anything. And now what I want to do is let's just move this over as well. So I don't want x8 to come all the way over here. Let's just make it come over here. right? And same thing, this thing, let's just move it over here. So x7 doesn't need to enter this far downstream. It can enter like this, right? And now we'll just switch the order like we were talking about over there, right? So now what you got here is you got a plus plus, and then a plus minus. Great. Okay, so that's all equivalent here. Let's go ahead and now erase the red box here. So still, we're doing great. We still have not changed the input-output relationship of the block diagram. So now you're seeing this is cleaning up quite nicely here. Okay, great. All right, so let's keep on rolling. So now let's talk about modification number 6 here. Let's keep going. What's the next thing we want to do to this block diagram to simplify it? Okay, so modification number 6 here, right? Let's go ahead and eliminate the feedback loop. Okay, so what I mean by that here is, let's isolate, here is a feedback loop. Okay, so this is a section I want to isolate. And also, to make this our lives a little easier, you can almost imagine that this here, there's a block here which is just like an identity, or a 1. Right? Because if that's the case, this looks exactly like we did earlier, right? Earlier you saw that if you had a feedback loop, I'm just redrawing a little section down there, G2, G1, H, right? We saw that this thing was exactly equivalent to a single block here, where you had what? You had this thing plus 1 inverse, right? Times this, right? So in other words, we saw that using the feedback mechanism, right? This is just going to be identity plus, right? G2, G1, inverse times the identity, times 1, right? Great, so we can replace this entire thing by this quantity, this single block, right? Great, let's do that. So erase everything inside the red and replace it with a single block which was, in our case, whoops, where did I put this thing? Yeah, here. So this is identity plus G2, G1 of S, H of S, inverse. Let me get a little bit more room so we can draw this thing cleanly. Inverse times the identity matrix, or I guess you can really just get rid of this identity if you want. Right? Great. We're almost done here, so I'll get rid of this. Okay. All right, almost there here. So the next thing here, let's do modification 7. Let's go ahead and eliminate the feed forward loop. Right, so you look here, we see that this is exactly the feed forward loop that we talked about earlier, right? Isolating the pertinent blocks, right? If we just draw this thing, we got a G2, G1, and then you got an upper path, which is just G2, and these things come together in a summing block like such, right? That's what's drawn inside the red dashed line. And from our discussion earlier, we saw that this thing is exactly equivalent to a single block where you just combine the two here, or add the two. So this is G2 plus G1, or sorry, G2, G1, right? Those are the same things here. Great. So let's replace everything in black or in red with just this single block. Okay, so this is a single block, which is G2 plus G2, G1. Great, and then let's erase the red. And look at this, we are almost done. Okay? Because the last mod, so modification number 8 here, is just, again, one of our good old friends combined in series. Right? So here's two blocks that are just in series with one another. So just to be consistent with how we've been doing this, let me just redraw the section inside the red dashed line. So we got a G2 plus G2, G1, followed with a identity plus G2, G1H inverse, right? And we said that this thing is exactly equivalent to a single block. Maybe I'll make sure I got this thing big enough. This is now this thing multiplied by this. So it is now identity plus G2, G1H inverse times G2 plus G2, G1. Input, output. Great. So I think we're done here in the sense that if I can now replace everything in red with a single block which is, we said, identity plus G2, G1, H inverse times G2 plus G2 times G1. There we go here. And then if I erase the red, I think we're done. Because now what we've got through these series of, it looks like 8 modifications here, is we have an equivalent, oh, sorry, I should have closed this thing, right? This, let's call T of S, right? This is our equivalent closed loop transfer function. So what you can do is you take any one of, it doesn't matter what the original G1, G2, and H were here. If you want to smash that entire original block diagram down to a single block, this is how you do this, right? So you know what I want to do here is let's check this actually in Matlab. So what I want to do in Matlab here to continue this example, let's just go ahead and choose some random G1, G2, and H's, and we'll build this thing in Simulink and using individual blocks, and then we'll check to see if this equivalent single transfer function behaves the exact same way here, right? So just for giggles, maybe it's easier for me to write this up. Let's pick some of these things. So for example here, I think the G1 I'm going to use here, something kind of complicated. It's, let me see here. I just want to make sure I get this proper. 3 times S plus 2, S minus 3 all over S plus 2, S plus 3, S plus 4. Okay, so here's my G1. Here's my G2 of S. Is going to be like, I don't know, -2. And again, I'm using something pretty complicated just to show that this doesn't matter here, how complicated these initial transfer functions are. If we did the math correctly, this should all follow through and it should all work here, right? So here, S squared plus 2S plus 5. And then finally for an H, let's just go ahead and use 3S squared plus 2S plus 5 all over S plus 1, S plus 2, S plus 4, S plus 6. Okay, so these are the individual original subtransfer functions, and we claim that if you take all these, stick it into this formula, and actually we'll do this in Mathematica because boy, I don't want to do all these multiplications and simplifications by hand. I'd rather have Mathematica do that here. But let's run over to the computer and see that we get the exact same thing in both cases. This single block versus the original complicated block diagram that we put together. Okay, so let's pause the video and run over to the computer. Alright, so here we are in Mathematica, and just to save you the trouble of watching me try to fat finger and type in these incorrectly, I've already got these input here into Mathematica here. So I just pre-typed in, here's what the G1 that we're using, the G2 that we're using, and the H that we're using here for our example. So let's just go ahead and shift enter, then get these into Mathematica. Okay, so the next thing that we probably want to do here is actually, let's go and expand the numerator and denominator of each of these so we can easily put them into Simulink. So again, hopefully you watched the video on transfer functions earlier in where we talked a little bit about how to get these into Matlab and Simulink here, and we saw that we need them in polynomial order here. So not in factored form, but I would like them in descending powers of s here. So for example, for G1, let's just go ahead and get the numerator of G1. Maybe I'll put this in a variable called G1 num here, and let's also get the denominator of G1, denominator of this, and you know what we should probably do is let's go ahead and expand these as well here so that they're not in factored form. Here we go. So here's what we can now put into MATLAB and Simulink when we go over there in a second. We see the numerator coefficient is just going to be a 3 and then a -9, and the denominator coefficient vector will be a 1, 7, and then 12. Let's go ahead and do the same thing for the rest of them here. So let's do G1, and then we're also going to want to do G2. Let me go ahead and just quickly change all these. G2, 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 and then Shift Enter. And let's also do the same for H. So we need the H numerator and the H denominator. Okay. All right. Oops, sorry. Not H1, just plain old H. Okay, so here we go. So here's all these individual transfer functions in a polynomial order here, right? Okay, so now the next thing that we want to probably do here is let's go ahead and compute what we claim to be the closed loop transfer function here. So let's just go ahead and write ourselves a little comment here of compute the closed loop transfer function. And if you recall, what we said and what we derived here on the board is we said that, all right, T of S is actually going to be what? It's identity plus G2, G1, H inverse times G2 plus G2, G1, right? That's what we derived on the board here. And whoops, I guess I should, let me match the braces appropriately. Square brace here. Or, yeah, you know what? Maybe it looks better with parentheses. Let's just go make these normal parentheses. I think we all get the point. Okay, so let's just go ahead and do that then. So we said that the closed loop transfer function T here, it's just going to be, in our case, we don't need an identity matrix. We just have a 1 here, right? Because these are all scalars. So this is 1 times plus G2 times G1 times H inverse times G2 plus G2 G1, right? And there we go, and maybe what we should do is let's go ahead and simplify this. Okay, so this theoretically is the closed loop transfer function of the entire system here. And again, let's do the same thing in the sense we want to get this thing in a polynomial form here, right? So again, let's simplify / rewrite in polynomial form so we can put this into Matlab / Simulink easily, right? Okay, so what I mean by that here is let's do this exact same thing we did up here, except let's just get the numerator and denominator coefficients here for the closed loop transfer function in expanded format. So there we go. We see that, yep, it's an 8th order and 7th order, and there's a lot of constants in here, but hopefully this will be easier now that we did this in Mathematica, and we can now just run over to MATLAB and input these. So let me go ahead and pause the video, and I'll switch over to MATLAB. Okay, here we are in Matlab, and again, to save time and avoid me making transcription errors while I punch it in on camera here, I've already entered in all of the coefficients here. So again, these coefficients, you'll remember, just came from our Mathematica notebook where we had already gone ahead and computed the coefficients for the G1 numerator. You can see them here. Here's a the G1 denominator, G2 numerator, G2 denominator, etc., etc. And you can hopefully see these are all correct, especially if we scroll all the way down to where we calculated the numerator and denominator coefficients for the closed loop transfer function T here. They were these large numbers here, but as you can see, we've faithfully input those into MATLAB. So we can represent the transfer functions in MATLAB using these vectors here. So with that being said, let's just go ahead and run this file here. So I'll run this so I have all of these numerator and denominator coefficient vectors defined. Now what I can do is let's just come over to Simulink here, start ourselves a blank model, and just go and grab some of those transfer function blocks and build the system that we had earlier. So maybe let's first make this one g1 of s, right? So in order to make this represent g1, what we need to do is call this g1 num and come on, g1 den, right? So here we go. Here's g1. Let's do the same thing for g2. So I just need to change this now to g2, right? And then g2. And then finally, we need h, I believe, was our last one. So I will change the coefficients here to be h and h. Great, so here's our blocks. So now all we have to do is just start stringing these things together like we had in the original block diagram here. So let's just go ahead and do that now. So I think I'm going to need a summing block here. So I'll come here to math operations here, grab a sum. Go ahead and change this to a plus minus. Whoopsies. That's exactly why I don't try not to do this on camera. I end up pushing all kinds of buttons here. Okay, so I think that got connected together. What else do I need? I need another summing block here, and I want this to actually be plus plus, and let's flip it so that it has an input on the top like such. Okay, I think that can get connected, and then that can get connected. And then over here, I think we had a feed forward path like that. Come on, touch that. Ah, shucks, come on. Connect. Connect, nope. Hold on, let me try that again. Branch off and then connect. Why is this thing not connecting? Uh-oh. Ha! Great, I have some kind of weird... Tell you what, let's keep building this and see if I can fix that in a second here. Okay, so let me go ahead and flip this block the other direction here so we can connect. The H, I think, came all the way back like this. Maybe what we should do is let's put a source. Maybe that's will help this. Let's just pick a, how about a sine wave? Let's just pick a sine wave here, connect this to the input here. And now let's see if we can branch this off. There we go. All right, so I'm gonna hope nothing was too serious there. Okay, so this is what we claim is the original transfer function, right? And then what we had was we claimed that the equivalent was this thing called t, right? And we said that it should be the same as that complicated transfer function up top is if we had just used that single block diagram down below. So you know what we should do? Let's put the input into both. This is the original one up top, right? And then down below is the more complicated, the simplified single equivalent block, right? Both of these red outputs should be identical if we did everything correctly. So to test that, let's just go ahead and grab a mux here. So I'm going to grab a mux here, join this up like such. Let's connect this here and connect this here. And hopefully if we did this correctly, these things are the same. So now let's just put these into a sync here of just some scope and connect these together. And there we go. We should be off to the races. Let's go ahead and move this over here and just hit play. And it ran. Let's check the outputs here. And voila, here we go. So you see, these are two signals that are exactly identical and sitting on top of each other here. So we see that this entire complicated block diagram up top is the exact same as this single compressed block down below. So I think this illustrates how we can use block diagram algebra to take something complicated and compress it and simplify it down to a single block here, right? Okay, so I'll tell you what, let's take a quick summary of what we covered today in this lecture. All right, so to summarize what we talked about today, we first started out by introducing what is a block diagram or a signal flow diagram. We then looked at different components that make up a block diagram, namely, mostly they were blocks which represented individual smaller subsystems, but you could also have things like branch points or summing nodes as well. And then we looked at the most important part of block diagrams, which was block diagram algebra or block diagram reduction here. So we looked at different operations that you can do on a block diagram to combine or simplify the signal flow chart. And then finally, we spent a good bit of time looking at an example of doing this block diagram reduction on a semi-complicated system. And we also looked at how to implement or check this reduction here in Mathematica as well as Matlab and Simulink. So, with that being said, I think that brings us to the end of the lecture today. I hope you enjoyed the discussion here. If so, please subscribe to the channel here. We'll have multiple other topics on control systems engineering in the short future. And I hope to catch you at one of those videos. Until then, talk to you later. Bye.